There's a quiet magic in places that remember, where the earth itself holds onto stories too ancient for books, too vast for human memory. Picture this, a single tree, its rings counting centuries like pages in a diary, or a layer of ice trapping air from a time when mammoths still roamed. These aren't just landscapes, they're living archives, whispering secrets of a world long before ours. And the most extraordinary part, they've been right here all along, hidden in plain sight, waiting for us to listen. Think about the last time you walked through a forest or stood by a canyon's edge. What if I told you that beneath your feet, in the very soil and stone, lies a record of everything that's ever happened there? From volcanic eruptions that shook continents to gentle rainfalls that nurtured forgotten forests, the Earth has been keeping score. These natural archives don't just tell us about the past, they help us understand the fragile balance of our planet today and what it might face tomorrow. So how do these silent witnesses hold onto so much? It's not just luck or chance. Nature has its own ways of preserving the extraordinary, fossilized pollen that reveals ancient climates, cave formations that map millennia of rainfall, even the chemistry of ocean sediments that remember when the seas were younger. This isn't just science, it's a detective story written in rock, ice, and leaf. And as we peel back the layers together, you'll see how these hidden records connect to everything from the air we breathe to the very ground beneath our cities. Ready to uncover the places where Earth never forgot? Let's begin. The oldest library on Earth isn't made of paper and ink, it's written in sunlight and stone. Take tree rings, for example. Each one is a snapshot of a year's struggles and triumphs. A narrow band might whisper of drought, while a thick one sings of abundant rain. But these aren't just solitary records. A single tree can tell us about its own life, but a forest of them, spanning centuries, reveals something far grander, the heartbeat of an entire ecosystem. Now imagine scaling that up. Sediment layers in lake beds stack like pages in a book, preserving pollen, ash, even tiny fossils that together sketch a portrait of ancient climates. And then there's ice, nature's most patient scribe. In places like Greenland and Antarctica, ice cores trap bubbles of air from thousands of years ago, letting us literally breathe the atmosphere of the past. What makes these archives so extraordinary isn't just their age, it's their honesty. A human historian might bend the truth, but a layer of volcanic ash doesn't lie about when the eruption happened. Coral reefs growing slowly over centuries record ocean temperatures in their skeletons with pinpoint accuracy. These natural record keepers don't have agendas, they simply are. And that's why scientists treat them like treasure maps. By cross-referencing tree rings with ice cores or matching sediment layers to coral data, they piece together a story far richer than any single archive could tell alone. It's like assembling a planetary jigsaw puzzle where every fragment, whether it's a speck of dust in ice or a chemical signature in rock, is a vital clue. But here's what's truly humbling. These archives weren't left for us. They exist because the Earth, in its endless cycles of growth and erosion, couldn't help but remember. A river carves a canyon and exposes rock layers that predate dinosaurs. A melting glacier releases logs from a forest that flourished when humans were first inventing the wheel. These records were here long before we knew how to read them, and they'll endure long after we're gone. That's the real magic, not just that the Earth remembers, but that it's always been willing to share its stories. We just had to learn how to listen. Imagine running your fingers along the weathered trunk of a bristlecone pine. some of these gnarled giants have stood silent witness to over 5,000 years of history. Each groove in their bark, each twist in their shape, tells a story written in the language of growth and survival. But the real magic lies beneath the surface, in those deceptively simple rings. A wide, bold ring might speak of a year when rains came generously, sunlight was plentiful, and the tree thrived. A tight, cramped one could whisper of cold summers, relentless droughts, or even the shadow of a volcanic eruption dimming the sun's warmth. What's astonishing isn't just that trees record their own lives, it's that they document the world around them. Take the infamous eruption of Mount Thera in the Aegean, a cataclysm so powerful it reshaped civilizations. For centuries, historians debated exactly when it happened. Then, dendrochronologists, those detectives of tree rings, found the answer in the stressed, stunted growth of ancient trees from that very era. Suddenly, these silent observers became precise timekeepers, aligning natural events with human history in ways no written record could. But trees don't just mark disasters. They're meticulous chroniclers of everyday change. The chemistry locked in each ring holds clues, traces of rainfall patterns, shifts in temperature, even evidence of long-vanished air quality. A single oak in Europe might carry echoes of medieval farming practices in its rings, while a sequoia in California could reveal how indigenous fire management shaped entire landscapes. And when scientists compare rings across continents, something remarkable emerges: a global conversation. A drought recorded in a Mongolian pine might mirror a famine described in Egyptian scrolls, linking distant corners of the world through the shared language of growth and scarcity. Here's the beautiful irony: these arboreal archives owe their clarity to adversity. A tree living in perfect conditions would grow uniformly, its rings blending into an unreadable blur. It's the struggles, the harsh winters, the dry spells, the recoveries, that carve the most vivid stories into their wood. Like a diary where only the extraordinary days are underlined, tree rings highlight the moments that mattered, both to the tree and to the world it inhabited. And as we learn to read them, we're not just decoding the past, we're holding a mirror to our own era's challenges, written one ring at a time. Deep in the heart of glaciers and ice sheets, time doesn't just pass, it gets trapped. Imagine holding a cylinder of ice older than human civilization, its layers compressed like the pages of a diary written in frozen ink. These ice cores are more than just frozen water. They're snapshots of ancient skies, capturing bubbles of air sealed away before the pyramids were built. Each layer tells a story: dust from long-dead volcanoes, chemicals from vanished oceans, even traces of pollen carried by winds that blew when woolly mammoths still walked the earth. Take the Vostok ice core, drilled from Antarctica's icy depths. It's a staggering time machine stretching back 800,000 years. Within its layers, scientists found something revelatory: a rhythmic pulse of ice ages and warm periods, like Earth's steady heartbeat. But the real treasure lies in those tiny bubbles. When researchers cracked them open, they released air from a world untouched by smokestacks or exhaust pipes, air that revealed carbon dioxide levels far lower than today's. Suddenly, we had proof written in ice. Our planet's climate has never changed this fast, this dramatically, without a helping hand from humans. What makes ice cores so extraordinary is their precision. A single year's snowfall can leave behind distinct markers: ash from a distant eruption, a spike in sea salt from stormy winters, or pollutants like lead from ancient Roman smelters. It's all there, frozen in place. Even more astonishing, ice doesn't just record the atmosphere, it remembers temperature. By analyzing the chemistry of the ice itself, specifically the weight of oxygen atoms locked within, scientists can reconstruct temperatures from millennia ago with startling accuracy. A warmer year leaves a different isotopic signature than a cold one, turning each layer into a thermometer for the past. But here's the humbling truth: these icy archives are vanishing. As global temperatures rise, glaciers melt, and with them go irreplaceable records. In the Alps, cores drilled just decades ago already show layers distorted by warming. Like a book left out in the rain, its ink bleeding together. It's a race against time to recover these frozen libraries before they're lost forever. Because once they're gone, there's no backup. No other record captures the whispers of ancient air quite like ice. And without it, we'd be left guessing at the very patterns that could help us navigate the climate challenges ahead. So the next time you see a snowfall, think of it as a page in progress. Each flake carries traces of the world as it is right now, a world future scientists might one day study, just as we peer into the ice of ages past. The difference is, this time we're writing the story. The question is, what will it say beneath the glassy surface of ancient lakes and the vast plains of ocean floors? Earth keeps another kind of diary, one written not in rings or ice, but in layers of silt and sand. These sediment archives pile up year after year, century after century, each stratum a time capsule waiting to be opened. Picture a single spoonful of mud from the bottom of a quiet lake. Within it, you might find pollen from forests that vanished millennia ago, microscopic shells of creatures long extinct, even flecks of ash from volcanoes that darkened skies before recorded history began. Now imagine scaling that up. In Japan's Lake Suwaijutsu, the sediment layers called varves are so precise they resemble tree rings, each pair of light and dark bands marking a single year. Over 52,000 years of history are pressed into those muddy pages, offering a timeline so accurate it's used to calibrate other dating methods worldwide. But what makes these layers truly remarkable isn't just their age, it's their versatility. A single core drilled from the lakebed can tell us about everything from rainfall patterns to the rise of human agriculture, all from the silent testimony of pollen grains and charcoal fragments trapped in the muck. And it's not just lakes, ocean floors are master archivists too. Take the white cliffs of Dover, those iconic walls of chalk. They're made almost entirely of ancient plankton skeletons, stacked over millions of years. Within them, tiny fossils and chemical traces reveal shifts in ocean temperature, acidity, even the comings and goings of entire marine ecosystems. Elsewhere, layers of volcanic ash act like bookmarks in Earth's story. When scientists find the same ash preserved in sediment cores from different continents, it's like discovering matching paragraphs in separate diaries, proof of a shared global moment frozen in time. Here's where sediment layers become detectives of human history. In the soils of Europe, a sudden spike in ragweed pollen signals the arrival of farming, as cleared land gave the weed room to thrive. In the Americas, layers rich in maize pollen trace the spread of indigenous agriculture, while traces of lead in Roman-era sediments expose the ancient world's industrial footprint. Even catastrophic events leave their marks. The asteroid that wiped out the dinosaurs left a telltale layer of iridium-rich clay, a dusty "the end" scrawled across the geologic record. But sediment archives have a quiet urgency to them. Unlike ice cores which vanish with melting or tree rings limited to a few millennia, sediments can stretch back millions of years, yet they're often overlooked. A single dredging operation or deep sea trawl can obliterate layers that took centuries to form. That's why scientists race to extract these stories while they're still legible, knowing each core pulled from the mud is another chapter salvaged from Earth's grand, unread library. And as we learn to translate them, these stratified diaries don't just recount the past, they whisper warnings, lessons, and even hope for the future written in the language of dust and time. Imagine walking through a forest where the trees aren't made of wood, but stone, where every log, branch, and leaf has been frozen in time, transformed into glittering quartz and agate. This isn't fantasy, it's the reality of places like Arizona's Petrified Forest, where entire ecosystems from over 200 million years ago have been preserved down to the cellular level. These aren't just fossils, they're time capsules capturing moments when dinosaurs still roamed among towering conifers and ferns, and the secret to their incredible preservation. A perfect storm of geology and chemistry. When these ancient trees fell, they were quickly buried by volcanic ash or sediment, sealing them away from oxygen and decay. Over millennia, mineral-rich groundwater seeped through their cells, replacing organic matter molecule by molecule, with silica essentially turning wood into stone. The result, logs that still show the grain of bark, the rings of growth, even the scars of prehistoric insect damage. It's as if nature hit pause on decomposition, giving us a window into a world we'd otherwise never see. But the real magic lies in what these petrified forests reveal. Take Antarctica's fossilized rainforests, yes, rainforests where today's icy wasteland was once a lush green wilderness. The presence of tree ferns and ginkgos in those stony remains tells us the continent was once warm enough to support sprawling forests, back when it was part of the supercontinent Gondwana. These fossils aren't just curiosities, they're proof that Earth's continents have wandered, climates have flipped, and life has adapted in ways we're only beginning to understand. Even the colors tell a story. The vibrant reds, yellows, and purples of petrified would come from trace minerals like iron and manganese, elements that seeped in during fossilization. A log with streaks of crimson might hint at iron-rich waters from ancient volcanic activity, while deep blues could point to manganese deposits from long-vanished seas. It's a rainbow of geological history, each hue a clue to the conditions that shaped these stone forests. And then there's the puzzle of how these forests fell in the first place. In some petrified deposits, trunks lie scattered like matchsticks, all pointing the same direction, a silent testament to prehistoric hurricanes or floods that flattened entire landscapes in moments. Other sites show trees fossilized upright, roots still gripping the stone, as if frozen mid-growth by some sudden cataclysm. These snapshots of disaster are eerily precise, letting us reconstruct ancient weather events with startling clarity. What's humbling is realizing these stone forests weren't meant for us. They're accidents of geology, moments of preservation so rare that for every petrified log we find, countless others have crumbled to dust. Yet here they stand, monuments to resilience and time, reminding us that even the mightiest forests can become stone, and that Earth's memory is far older and far stranger than we often imagine. Beneath the shimmering surface of tropical seas, coral reefs do more than dazzle with their colors. They keep meticulous records of the ocean's past. Each year, as corals grow, they add a new layer to their limestone skeletons, trapping tiny chemical signatures within. These bands, much like the rings of a tree, become a living ledger of the sea's history. The temperature of the water, the intensity of storms, even the acidity of the ocean, all are etched into their stony embrace with near-scientific precision. Take the massive porite corals of the Great Barrier Reef, some of which have been growing for over 400 years. When scientists drill into these ancient giants, they're not just extracting rock, they're pulling up pages from an underwater diary. The chemistry of each layer tells a story. A year of unusually warm water might leave behind a distinct isotopic signature, while traces of heavy metals could hint at long-ago industrial runoff. Some corals even preserve evidence of forgotten hurricanes, their growth bands disrupted by the churning of powerful waves. What's astonishing is how these records challenge our assumptions. Long before modern instruments began tracking ocean temperatures, corals were quietly documenting them. In the Caribbean, centuries-old brain corals reveal a pattern of warming that predates industrialization, offering clues about natural climate cycles. Meanwhile, in the Pacific, fossilized corals from the last ice age show how drastically sea levels have risen, their ancient tops now stranded high above today's waterline, like stone bookmarks in a flooded library. But corals don't just record the past, they react to it. Bleaching events where stressed corals expel their colorful algae leave ghostly white bands in their skeletons. By studying these pale scars, researchers have identified bleaching episodes that occurred long before the term was even coined. A coral head in Florida might show a series of bleached layers from the 1930s, corresponding to historical droughts, while Australian reefs bear the marks of 19th century heatwaves. These aren't just abstract data points, they're urgent reminders that the oceans have been sending signals for centuries. We're only now learning to read them. The real power of coral archives lies in their global reach. Unlike tree rings or ice cores, which are bound to specific regions, reefs span the planet's tropical waters, offering synchronized records from multiple oceans. When a major volcanic eruption like Krakatoa's in 1883 darkened skies worldwide, corals from Indonesia to the Caribbean captured its cooling effect in their chemistry. It's as if the entire ocean were taking notes, waiting for us to piece together its story. Yet these underwater chronicles are at risk. As oceans warm and acidify, many reefs are dying before their full histories can be recovered. Some of the oldest corals, those with memories stretching back to the Little Ice Age or the medieval warm period, are now succumbing to modern stressors. It's a race against time to extract their stories before they're silenced, to listen, while we still can, to what these ancient witnesses have been trying to tell us all along. Because once they're gone, so too is a unique archive of our planet's past, written in stone and sealed beneath the waves. Some of Earth's most revealing stories aren't written in stone or ice, they're carried on the wind. Picture vast plains of fine, golden silt piled hundreds of feet deep, each grain a tiny messenger from the past. These are lowest deposits, Earth's wind-blown archives, where the very dust under our feet holds clues to ancient skies, lost landscapes, and the rise of civilizations. Take China's lowest plateau, a sprawling landscape built almost entirely of this airborne sediment. Over millions of years, winds lifted fine particles from distant deserts and riverbeds, depositing them layer by layer. But here's what's extraordinary. Trapped within those layers are snapshots of the world as it was. Pollen grains whisper about forests that once thrived where there's now only dust. Chemical signatures in the soil reveal periods of heavy rainfall or crushing drought. Even the size of the silt particles tells a story. Finer grains suggest gentler winds, while coarser ones hint at howling storms that reshaped entire regions. What makes Loess so remarkable is its connection to human history. In China, the fertile soils derived from these deposits became the cradle of early agriculture, nurturing millet and wheat crops that sustained dynasties. But dig deeper and the layers reveal a cautionary tale. Sections of the plateau show abrupt shifts, thick, dark soil suddenly giving way to pale, loose silt. These are the fingerprints of climate change events that turned lush farmland into dust bowls, forcing ancient communities to adapt or migrate. It's as if the land itself kept a diary of civilization's triumphs and struggles, written in the language of erosion and regrowth. Halfway across the world, the American Midwest tells a similar story. The lowest deposits blanketing Iowa and Nebraska didn't just create some of the planet's richest farmland, they preserved a timeline of the Ice Age. As glaciers retreated, they ground rock into powder, which fierce winds carried south. Within these layers, scientists find volcanic ash from eruptions that darkened skies 12,000 years ago, and buried soils that prove entire ecosystems rose and fell between ice ages. Some sections even hold traces of early human activity: charcoal from long-extinguished campfires, or stone tools dropped by hunters pursuing mammoths across a very different prairie. But perhaps the most surprising thing about Loess is how alive it is. Unlike static rock formations, these deposits constantly interact with the atmosphere. The same winds that built them still reshape them today, carrying dust from the Sahara to fertilize the Amazon, or swirling topsoil from Dakota fields across entire continents. Modern sensors can track these journeys in real time, but the ancient layers remind us this isn't new. Earth's atmosphere has always been a restless librarian, endlessly rearranging its dusty volumes. The next time you see a cloud of dust dancing on the breeze, consider this: those tiny particles might one day settle into a layer that outlasts mountains. They'll carry whispers of our time: the chemicals from our farms, the soot from our fires, the pollen from our vanishing forests. Long after we're gone, the wind will keep writing its memoirs, one golden grain at a time. Deep beneath the Earth's surface, where sunlight never reaches, time moves differently. Here, drop by drop, water carves its way through limestone, leaving behind sculptures that double as climate diaries. Stalactites hanging like stone icicles and stalagmites rising like silent sentinels aren't just cave decorations, they're archives, growing at a pace that makes tree rings seem hasty. A single inch of these formations might represent 1,000 years of patient deposition, each layer encoding the chemical secrets of the world above. Take a cave in Borneo, where speleothems, the scientific term for these mineral formations, hold clues to the planet's tropical past. As rainwater filters through soil and rock, it picks up traces of elements like oxygen and carbon, which then freeze into the growing stone. The ratio of oxygen isotopes in each layer acts like a fingerprint, revealing whether the climate was wet or dry when that drop fell. Some caves even preserve evidence of ancient monsoons, with growth spurts corresponding to periods of heavy rainfall. It's as if the Earth itself kept a ledger of every passing cloud. But the real magic lies in how these formations bridge gaps in our understanding. Ice cores can't form in the tropics, and tree rings only go back so far. Speleothems, though, thrive in places where other archives vanish. In the caves of Oman, stalagmites have chronicled the rise and fall of the Arabian Green period, a time when deserts bloomed into grasslands. Their layers show abrupt shifts from wet to dry, mirroring changes in human settlement patterns, proof that climate and civilization have always been intertwined. What's astonishing is the precision. Modern lasers can scan stalagmites slice by slice, detecting variations as fine as a single year's weather. A particularly dry decade might leave behind a band of dense, slow-growing calcite, while a volcanic eruption, like Indonesia's Tambora in 1815, could deposit a spike of sulfuric acid captured mid-fall. Some formations even trap ancient air pockets, preserving traces of methane or carbon dioxide from millennia ago. It's climate science written in a language of water and stone. Yet these subterranean records aren't just about the past. By revealing how ecosystems responded to ancient droughts or warming events, they offer glimpses of what might lie ahead. A stalagmite from a New Mexico cave, for instance, shows that the region's megadroughts of the medieval era lasted decades longer than previously thought, a sobering insight for today's water managers. Other speleothems hint at tipping points, moments when rainfall patterns flipped abruptly and never fully recovered. The quiet beauty of these cave chronicles is that they were never meant to be read. They grew in darkness, undisturbed, recording every drip without bias or agenda. Now, as scientists illuminate their hidden pages, we're learning that some of Earth's most honest history books weren't written on parchment or papyrus. They were written in the patient language of falling water and time. Imagine a tiny, furry archaeologist with a compulsive hoarding habit. That's essentially what a Packrat is. These unassuming rodents, scurrying through the deserts of the American Southwest, have been unknowingly building some of the planet's most precise natural archives. Every time a Packrat drags a twig, a leaf, or even a bone back to its nest, it's not just gathering supplies, it's curating a snapshot of its ecosystem. But here's where it gets extraordinary. These nests, called middens, aren't just temporary shelters. Over centuries, the Packrat's sticky urine crystallizes into a glue-like substance called amberat, encasing everything in a hardened, climate-proof shell. What starts as a rodent's cluttered bedroom becomes a fossilized time capsule, preserving plants, pollen, and even insect remains with stunning clarity. One of the most astonishing discoveries came from Nevada's Great Basin, where scientists cracked open a midden older than the Egyptian pyramids. Inside, they found fragments of juniper and pinyon pine species that haven't grown in the region for millennia. This wasn't just a list of ancient plants, it was a puzzle piece revealing how drastically the landscape had changed. By comparing middens from different eras, researchers traced the gradual retreat of these trees as the climate grew drier, painting a portrait of an ecosystem in flux. But the real surprise, some middens held traces of plants that no longer exist anywhere on Earth, their only record preserved in the hoarding habits of a long-dead rodent. What makes Packrat middens so invaluable is their specificity. Unlike sediment layers or ice cores, which blend years together, each midden captures a narrow window of time, sometimes just a single rodent's lifetime. Open one and you're peering into a precise moment, a drought summer marked by shriveled leaves, or a wet season where lush grasses dominated the collection. Even more telling are the items Packrats borrowed from humans: bits of pottery, woven fibers, or food scraps which stitch these natural records directly into the story of ancient cultures. A midden near an ancestral Puebloan site might hold corn kernels alongside wild seeds, revealing how human diets intertwined with the local flora. The sheer durability of these nests defies expectation. Some have survived 40,000 years, sheltered in rocky crevices where even the slow grind of erosion couldn't reach them. Inside, delicate materials like flower petals or feathers remain intact, their colors long faded but their structures pristine. It's as if the Packrats were tiny museum curators, selecting and preserving exhibits with a conservator's care. But perhaps the most poignant lesson from these middens is how much we owe to accident. The Packrats weren't trying to document their world for future scientists, they were just living their lives, gathering what they needed to survive. Yet in doing so, they created a library of life as it was, one sticky, haphazard page at a time. And now, as modern climates shift at unprecedented speeds, these accidental archives remind us that ecosystems have always been in motion, but never quite like this. The next chapter, it seems, is ours to write. There's something haunting about the way peat bogs remember, not with stone or ice, but with flesh and fabric. In the silent, watery depths of these wetlands, time doesn't just slow down, it stops altogether. The chemistry here is unlike anywhere else on Earth. Acidic waters, starved of oxygen, work like a natural embalming fluid, tanning skin to leather, preserving hair down to the last strand, even keeping the wrinkles on a brow frozen mid-expression for millennia. The result, bodies so intact they still look like they could sit up and speak. Take Toland man, discovered in Denmark with a rope noose still tight around his neck. His face, peaceful in death, carries the faint stubble of a beard shaved days before his execution 2,000 years ago. His last meal, a simple porridge of barley and flax, remains undigested in his stomach, a snapshot of an Iron Age breakfast. Then there's Lindo Man from England, his manicured nails and well-groomed hair hinting at high status, his stomach full of charred bread, perhaps part of a ritual feast before his violent end. These aren't skeletons or fragments, they're fully realized people, preserved with a clarity that makes history feel unnervingly close. But the real magic of bog bodies isn't just their skin and bones, it's what they carry with them. The very conditions that mummify humans also pickle their belongings. Woolen cloaks dyed vibrant colors, leather shoes stitched with precision, even butter packed in wooden tubs, still edible after centuries. These artifacts don't survive in ordinary soil, yet here they are, defying decay. Even more astonishing are the microscopic clues. Pollen grains clinging to a tunic reveal the season of death, spring blossoms or autumn weeds trapped in the weave. Beetle wings in the peat nearby tell scientists what the air temperature was when the body was laid to rest. It's as if the bog took a forensic photograph of the exact moment these people entered its depths. Peat bogs don't just preserve individuals, they archive entire ecosystems. The same acidic water that pickles human tissue also safeguards delicate plant matter, sphagnum moss, reeds, even fragile flowers, that would crumble to dust elsewhere. By studying these layers, scientists can reconstruct ancient landscapes down to the types of grasses that grew in a meadow or the insects that buzzed through the air. In Ireland's bogs, perfectly preserved oak timbers reveal precise construction methods of Neolithic trackways, while in Germany, bundles of sacrificial weapons emerge from the muck, their wooden handles still intact. What's chilling is how these bogs choose what to keep. They don't preserve everything equally. Bones often dissolve in the acidic brew, leaving behind eerily deflated skin sacs. Stomach contents remain, but muscle tissue might vanish. This selectivity creates a ghostly paradox, a face recognizable enough to reconstruct, but a skeleton nearly gone. It's as if the bog is editing history, deciding which stories get told and which fade away. Yet for all their mystery, bog bodies force us to confront uncomfortable truths. Many show signs of brutal violence, broken skulls, slit throats, even deliberate strangulation with ornate ropes. Some scholars believe these were sacrifices, offerings to gods we'll never fully understand. Others might have been criminals or outcasts, their deaths a form of justice. The bogs don't explain, they simply hold the evidence, leaving us to piece together motives across an unbridgeable gap of centuries. The most humbling realization, these people never intended to become time capsules. They weren't buried with treasure like Egyptian pharaohs or entombed in pyramids meant to endure. They sank into the mud by accident or design, forgotten until the peat cutters' spades uncovered them millennia later. Now, they're messengers from a world without written records, their very bodies proving that sometimes the Earth remembers best what history books never could. When Mount Vesuvius erupted in 79 AD, it didn't just bury Pompeii, it sent a layer of ash circling the globe, settling invisibly into soils, lake beds, and even distant ice sheets. Today, that same ash acts like a barcode in Earth's archives, a precise timestamp that lets scientists sync events across continents. But Vesuvius is just one entry in a much larger ledger. From the colossal eruption of Indonesia's Toba 74,000 years ago, which left traces from Africa to Antarctica, to the more recent Tambora event of 1815, volcanic ash layers are nature's way of pressing pause on the planet's chaotic timeline, giving us reference points in the fog of deep time. What makes these ash markers so invaluable is their universality. A shard of volcanic glass found in an Egyptian tomb can be chemically matched to an eruption in the Aegean, proving trade routes existed centuries earlier than written records suggest. In Greenland's ice cores, sulfate spikes from long-dead volcanoes align with tree ring anomalies in North America, creating a cross-continental harmony of data. Even more astonishing, some ash layers are so distinctive they're named like rock stars. The Y8 ash from a Mediterranean eruption 30,000 years ago shows up in caves across Europe, helping archaeologists date everything from Neanderthal tools to early cave art. The detective work doesn't stop at identification. The thickness of an ash layer tells a story too. A thin dusting in Germany might correspond to a thick blanket in Italy, revealing wind patterns of the ancient world. Grain size matters as well. Fine particles could mean the eruption plume reached the stratosphere, chilling the planet for years, while coarse grains suggest a more localized event. And then there's the chemistry. Each volcano has a unique geochemical fingerprint, like the high zirconium content in New Zealand's Taupo ash or the telltale barium spikes from Alaska's Aniakchak caldera. These aren't just layers, they're encrypted messages about Earth's explosive past. Perhaps the most humbling realization is how these fiery bookmarks connect human and natural history. The ash from Thera's eruption in the Aegean, a cataclysm some link to Atlantis myths, appears in Egyptian stratigraphy during the turbulent reign of Pharaoh Ahmose, hinting at how climate disruption may have shaped civilizations. In Iceland, layers from the Laki-Fissure eruption of 1783 coincide with historical accounts of famine as far away as Japan, proving how tightly the planet's systems are woven together. Even today, when researchers find traces of the 1883 Krakatoa eruption in European wine harvest records or North American snowfall logs, they're reminded that Earth's memory is written not just in rock, but in the ripple effects that touch every corner of the globe. Yet for all their precision, these ash layers carry a quiet warning. The same geologic forces that create these perfect time markers are still at work today, brewing beneath Yellowstone, Campi Flegrei, and other restless calderas. One day, future scientists may sift through layers of our own era, finding traces of microplastics or nuclear isotopes alongside volcanic deposits, and wonder how we read the clues left for us while writing so many of our own. The archives are there, waiting. The question is whether we're paying attention. Standing alone in a field or perched impossibly on a hillside, glacial erratics look like nature's practical jokes, massive boulders dumped where they clearly don't belong. These wandering rocks, some as large as houses, didn't roll or tumble into place. They were carried slowly and deliberately by rivers of ice that no longer exist. Take Norway's Big Rock, a 500-ton granite giant resting on limestone bedrock hundreds of miles from its homeland. It's as if a glacier plucked it from the mountains like a child pocketing a pebble, then absent-mindedly dropped it when the ice finally retreated. But these geological misfits aren't just curiosities. They're compasses pointing to Earth's frozen past. Every erratic carries a birth certificate in its mineral makeup. Match the rock's chemistry to distant outcrops, and suddenly you're tracing the path of ancient ice sheets like breadcrumbs. In North America, erratics from the Canadian Shield litter the Midwest, revealing how the Laurentide ice sheet bulldozed its way south during the last ice age. Some boulders even bear scars from their journey's parallel grooves scratched by bedrock as the ice dragged them along, or polished surfaces sanded smooth by countless grains of glacial grit. The real magic happens when erratics cluster. In Scotland's Train of the Dead, a string of boulders stretches for miles, marking where a glacier's conveyor belt dumped its cargo as it melted. In the Alps, distinctive pink granite erratics help reconstruct ice flows that shaped entire valleys. and sometimes these rocks become accidental time capsules. When glaciers pluck boulders from cliffs, they sometimes trap fragments of ancient soil or vegetation beneath them, preserving snapshots of landscapes that vanished under the ice. What's humbling is realizing how recent this all was. Many erratics were dropped just 12,000 years ago, a blink in geologic time. Indigenous oral traditions from the Pacific Northwest still recount when the ice retreated, describing landscapes transforming within human memory. Today, these silent travelers continue to shape cultures, from the legendary Judgment Rocks of Germany, where erratics were once believed to be thrown by giants, to modern artists who paint them bright colors to highlight their alien presence. Yet for all their weight and permanence, glacial erratics are fleeting markers. The next ice age will rearrange them again or grind them to dust. For now, they stand as reminders that even the mightiest stones are just passengers on Earth's great journey, hitchhiking across continents on frozen highways that come and go. The ocean has never forgotten where it's been. Its currents, those vast rivers within the sea, leave behind clues not in water but in stone. Take a handful of sediment from the seafloor, and you might find the key to an ancient map, one written in the language of shells and microscopic plankton. These tiny creatures didn't just live in the ocean. They carried its secrets in their very bodies, recording temperature, salinity, and even the speed of the currents that carried them. Now, long after their deaths, they've become timekeepers of the deep. Consider the humble forum, a microscopic plankton with a shell no bigger than a grain of sand. When alive, their shells absorbed chemical fingerprints from the surrounding water, specific ratios of oxygen isotopes that betray the temperature at the time they formed. After death, they sank to the ocean floor, layering themselves like pages in a book. By drilling into these sediments, scientists can read these chemical signatures and reconstruct currents from millions of years ago. A cluster of warm water species in what's now the frigid North Atlantic. That's the ghost of a long-vanished current, a highway of heat that once defied the poles. But the real surprises come from the wanderers, the fossils that shouldn't be where we find them. In the rocky cliffs of Norway, there are shells of creatures that today only thrive in the tropics. How did they get there? The answer lies in the great conveyor belt of the oceans. During the Eocene epoch, 50 million years ago, a powerful current called the Proto-Gulf Stream ferried warm water, and the life within it far northward, turning regions that are now icy into subtropical havens. Those stranded shells are like signposts marking where the currents once turned. Even more astonishing are the clues hidden in fossilized whale bones. Chemical analysis of these ancient remains reveals migration patterns shaped by currents that no longer exist. A whale that died in what's now the desolate Atacama Desert once swam through a lush, nutrient-rich current, its bones preserving isotopes from waters that flowed differently when the continents were younger. It's as if the whales themselves were mapping the ocean's past with every mile they traveled. The ocean's memory isn't just about temperature, it's about movement. Fossilized plankton shells from the same species, found continents apart, can reveal how fast ancient currents flowed. Thicker shells might indicate slower waters where organisms had more time to grow, while thinner, lighter ones suggest they were rushed along by powerful flows. In the Mediterranean, layers of fossilized algae tell of a time when the Strait of Gibraltar closed, turning the sea into a vast salt pan before the Atlantic burst back in. The fossils don't just record the event, they show how the currents scrambled to adapt. What's humbling is realizing how much we owe to these silent witnesses. Without them, we'd have no way to trace the ocean's ancient rhythms, no way to understand how currents shaped and were shaped by a changing climate. They remind us that the blue highways we see today are just a snapshot in a much longer journey. And as we face a future where those currents may shift again, these fossilized whispers from the deep become more than just history. They're a guide to what might lie ahead. Beneath our feet, hidden under layers of rock and time, lie forgotten landscapes not as fossils or artifacts, but as soils that once breathed with life. Paleosols, these ancient dirt layers, are more than just old ground. They're time capsules of vanished worlds, holding secrets in their chemistry, texture, and even their smell. Picture cracking open a paleosol from 50 million years ago and catching a whiff of something unexpected, not the sterile scent of stone, but the earthy aroma of a forest floor that hasn't existed for epochs. Take the Badlands of South Dakota, where wind and water have carved open the earth like pages in a book. Here, paleosols tell the dramatic story of a continental transformation. One layer might be thick with carbon, its dark hue betraying the lush, swampy forests of the Eocene, where giant titanothers lumbered through steaming undergrowth. Just a few inches above, the soil changes abruptly lighter, richer in silica, laced with the fossilized roots of grasses. This is the moment, frozen in dirt, when North America's heartland shifted from jungle to savanna, a change that would eventually give rise to the Great Prairies and the herds that roamed them. But paleosols don't just record what grew above them, they remember the sky. In Wyoming's Big Horn Basin, iron-rich paleosols from the Paleocene bear the rusty fingerprints of an atmosphere we'd barely recognize. Their chemistry suggests oxygen levels nearly 30% higher than today, a world where dragonflies the size of hawks took flight and forests grew with feverish intensity. Elsewhere, paleosols laced with volcanic ash reveal years without summers, their stunted plant traces hinting at global winters caused by eruptions halfway across the world. The real magic lies in the microscopic details. Buried in these soils are fossilized fungi, their thread-like hyphae still tangled around the ghosts of roots, preserving symbiotic relationships older than mammals. Pollen grains, smaller than dust motes, reveal floral communities long since displaced. In Australia, paleosols from the Cretaceous hold traces of proteins that suggest flowering plants evolved there millions of years earlier than previously thought, rewriting the story of botany itself. Perhaps most astonishing are the human connections. In the lowest plateau of China, paleosols interwoven with ash and charcoal document humanity's first experiments with fire-altered landscapes. In Africa, layers of soil sandwiched between volcanic deposits show where early hominins trod, their footsteps subtly altering the Earth's composition in ways that persist millennia later. These aren't just records of climate or vegetation, they're archives of influence, showing how life, from microbes to mankind, shapes the very ground it walks on. What's humbling is realizing how fragile these archives are. Exposed to modern air, some paleosols crumble within hours, their delicate structures collapsing after eons of preservation. Others, hidden beneath cities or farmland, are unknowingly plowed away or paved over. Yet those we've saved whisper urgent lessons. Their layers show how quickly ecosystems can transform, how resilient and how vulnerable life can be. They remind us that the soil beneath our shoes isn't just dirt. It's the accumulated memory of everything that ever grew, died, and returned to the earth. And if we listen closely, it might just tell us what comes next. Some of Earth's most delicate memories are written in stone that shouldn't exist, towering tufa spires rising from lakes like frozen fountains, or travertine terraces spilling down hillsides in creamy, mineral-rich cascades. These aren't just geological oddities, they're history books written in dissolved limestone, each layer a sentence in the story of water's endless dance with rock. Take Mono Lake's eerie tufa towers in California, which stand like ancient sentinels above the waterline. Their knobby surfaces, pocked with tiny voids, might look like coral reefs, but they're actually the work of underground springs. When calcium-rich groundwater meets the lake's alkaline waters, a chemical handshake occurs, transforming liquid into stone at a pace we can almost watch. What makes these formations extraordinary isn't just their beauty, it's their precision. Each band of travertine at Turkey's Pamukkale, for instance, records a moment when mineral-laden water slowed, warmed, or changed course. Thick layers might indicate centuries of steady flow, while thin, wavy ones hint at droughts or earthquakes that disrupted the springs. Even the color tells a tale. Pure white bands form when water runs fast and clean, while rusty streaks betray the presence of iron, carried up from deep underground during periods of volcanic unrest. It's as if the Earth took meticulous notes in a language of crystal and sediment. But the real magic happens at the microscopic level. Trapped within these stone layers are isotopes of oxygen and carbon, tiny chemical clocks that reveal the temperature and composition of the water when each layer formed. In Yellowstone's Mammoth Hot Springs, scientists have matched travertine deposits to known climate events, like the Little Ice Age, by reading these mineral signatures. Elsewhere, tufa formations in dry lake beds hold clues to vanished wet periods, their growth rings proving that deserts like Nevada's Great Basin were once lush with waterways. The most surprising detail: these formations aren't relics of the distant past, they're still writing their stories today. At Havasu Falls in the Grand Canyon, new travertine builds hourly as water tumbles over existing ledges, coating everything in a living veneer of stone. Meanwhile, in Croatia's Plitvice lakes, fallen leaves and twigs become fossilized within weeks as minerals encase them mid-decay, creating snapshots of ecosystems frozen in crystalline time. What's humbling is realizing how fragile these records are. A single shift in groundwater chemistry can stop deposition in its tracks, leaving half-formed towers as monuments to interrupted processes. At Mono Lake, diversion of water sources in the 1940s starved the tufa of their building blocks, halting growth for decades. Now, as conservation efforts restore balance, new stone slowly accrues, a reminder that these archives aren't just about the past. They're living proof that Earth's memory is still being etched, one mineral droplet at a time. Charcoal doesn't just burn away, it sinks into the earth, becoming a ledger of every flame that ever swept across a landscape. Dig into the soil of any fire-prone region, and you'll find these dark, gritty layers, stacked like the pages of a book written in soot. Each band tells of a specific blaze, its thickness hinting at the fire's intensity, its chemistry revealing what plants fueled the flames. In Australia's Blue Mountains, scientists have uncovered charcoal deposits dating back 40,000 years, chronicling fires that raged when humans first arrived on the continent. But these records aren't just about destruction, they're about cycles. Between charcoal layers lie stretches of clean sediment, quiet chapters where the land healed, grew lush, and prepared for the next inevitable spark. What makes these charcoal archives so revealing is their precision. Under a microscope, individual particles betray their origins. Fluffy, porous fragments might come from grasses that ignited in quick, hot fires, while dense, angular chunks could be the remains of ancient trees that smoldered for weeks. In the American West, researchers use this forensic detail to distinguish between natural lightning fires and those set by indigenous peoples for land management, a practice that once shaped entire ecosystems. The charcoal doesn't lie. In some regions, human stewardship actually reduced catastrophic burns by introducing smaller, controlled fires that cleared underbrush without devastating mature forests. The real surprise lies in how these records challenge modern assumptions. In Tasmania, lake sediments show that before European settlement, massive fires occurred only once every few centuries. But after colonization and the suppression of indigenous burning practices, charcoal layers became more frequent and erratic, reflecting the unstable fire regimes we grapple with today. Similarly, in California's Sierra Nevada, pre-colonial charcoal bans align with drought cycles, proving that fire was a natural and necessary part of the landscape long before Smokey Bear warned against it. Perhaps the most sobering insights come from comparing charcoal layers to climate data. In South Africa's Cederberg Mountains, sediments reveal that during past warm periods, fires burned twice as often as they do now, a glimpse of what might lie ahead as global temperatures rise. Yet these ancient layers also offer hope. Some ecosystems, like Australia's eucalypt forests, showed charcoal in every era, proving their resilience through millennia of flames. Their secret, adaptations like fire-resistant bark and seeds that only sprout after a blaze, turning destruction into rebirth. The lesson written in these ashy pages isn't just about fighting fires, it's about learning to live with them. As modern megafires reshape continents, these charcoal archives remind us that flames aren't the enemy, imbalance is. The Earth remembers every burn, every recovery, every mistake. And if we read closely enough, it might just teach us how to write a better future. There's a place on Earth where time stands still, not in a poetic sense, but literally frozen in place. Arctic permafrost, that thick layer of permanently frozen soil, acts like nature's ultimate deep freezer, locking away organic matter with such precision that fur still clings to mammoth skin, and the stomach contents of extinct wolves remain undigested after 12,000 years. In Siberia's Yamal Peninsula, reindeer herders occasionally stumble across creatures like the woolly rhino, their muscles and internal organs so well preserved they look like they could have died yesterday. These aren't just fossils, they're snapshots of an entire ecosystem suspended in ice. But the real treasure of permafrost isn't just the creatures it preserves, it's the microscopic world. Take the Yadoma permafrost of northeastern Russia, where ancient grass roots, pollen, and even bacteria lie dormant in icy tombs. When scientists thawed 30,000-year-old seeds from a squirrel's burrow, something extraordinary happened. They sprouted. Not only did the ice keep these plants intact, it kept their biological machinery ready to restart, as if someone had hit pause on life itself. Elsewhere, researchers have revived 40,000-year-old roundworms, their bodies thawing back to motion after millennia in stasis. It's like opening a time capsule where the contents are still alive. Yet for all its scientific gifts, permafrost holds a darker secret. Locked within its icy grasp are billions of tons of greenhouse gases, methane and carbon dioxide, accumulated over ages from decaying plants and animals that never fully decomposed. As temperatures rise and the Arctic warms twice as fast as the rest of the planet, these gases are bubbling to the surface in eerie phenomena. In some parts of Siberia, the ground literally breathes, swelling into methane-filled blisters that burst with enough force to leave craters 30 feet deep. Elsewhere, thawing permafrost is turning forests into drunken trees, their roots destabilized by melting ice, leaving them leaning at surreal angles. The scale is staggering. Permafrost soils contain nearly twice as much carbon as the entire atmosphere. When they thaw, microbes wake from their slumber and begin feasting on ancient organic matter, releasing gases that accelerate warming in a vicious cycle. But here's the twist: permafrost isn't just a victim of climate change, it's an active participant. In Alaska's North Slope, scientists track thermokarst lakes formed when thawing ice collapses the ground. These lakes, with their dark surfaces, absorb more sunlight than ice, further heating the surrounding permafrost and creating runaway feedback loops. What's humbling is realizing how quickly these frozen archives are vanishing. The same ice that preserved a 40,000-year-old foal in near-perfect condition is now melting fast enough to expose whole Pleistocene landscapes. In Canada's Yukon, gold miners blast through permafrost to reach bedrock, only to uncover Ice Age bones by the ton, a bittersweet bounty where scientific discovery races against industrial extraction. Meanwhile, indigenous communities who have lived atop these frozen layers for generations watch as their cellars flood, their roads buckle, and their hunting grounds transform into unfamiliar wetlands. Permafrost doesn't just remember the past, it's writing the future. Each thawing layer is a ledger of planetary changes, from the mammoths that once roamed its surface to the invisible gases now seeping into our atmosphere. It reminds us that some vaults once opened can't be closed again, and as we peer into these icy depths, we're not just uncovering lost worlds, we're glimpsing the fragile threads that bind Earth's memory to its destiny. A flint blade lying in the dust might seem like just a relic of human ingenuity until you realize it's also a love letter from the land itself. Every stone tool ever crafted carries a dual history, the story of the hands that shaped it and the deeper saga of the earth that provided the raw material. Take the obsidian spear points of ancient Mesoamerica, glossy black and sharper than surgical steel. Their presence in Mayan cities hundreds of miles from any volcano tells us more than just trade routes. It reveals entire chapters of geological history. The specific chemical fingerprint of each obsidian shard can be traced back to exact eruptions, mapping how lava flows millions of years ago set the stage for human commerce millennia later. But stone tools don't just reflect geology, they record scarcity and adaptation. In Britain's Boxgrove site, 500,000 years old, early humans meticulously recycled flint nodules, leaving behind cores whittled down to the size of walnuts. The closer you look, the clearer it becomes. They weren't being frugal, they were running out. The chalk cliffs that once supplied their raw material had retreated with rising seas, forcing these toolmakers to stretch every last fragment. Meanwhile, in East Africa's Olduvai Gorge, shifts in tool materials over time. From basalt to quartzite to chert mirror the changing landscapes as lakes dried up and rivers changed course, turning once abundant rock sources into distant memories. The real detective work begins when tools defy expectations. Why would Clovis people in North America haul jasper from Wyoming to Texas when local stone was available? The answer lies in Ice Age geography. Their migration routes followed vanished corridors between glaciers where certain rocks became cultural touchstones. Elsewhere, in Australia's Arnhem Land, Aboriginal tools made from exotic materials like rainbow chert reveal something astonishing. Seasonal trade winds were once predictable enough to facilitate cross-continental exchange networks, with stones passing hand to hand along routes that still echo in Dreamtime stories. Perhaps most poignant are the tools that mark environmental catastrophes. In the American Southwest, ancestral pueblones abruptly switched from fine-grained chert to rougher volcanic rock around the 13th century. At first glance, it seems like a step backward until you notice the corresponding drought signals in tree rings. With water sources gone, the knowledge of distant quarries faded, leaving communities to make do with whatever the parched land still offered. These aren't just artifacts, they're distress signals carved in stone. What's humbling is realizing these lithic archives were never meant for us. Early toolmakers weren't consciously documenting their world, they were simply responding to it, their choices constrained by glaciers they didn't understand, rivers they couldn't control, and rocks that told them where they could or couldn't go. Yet in their pragmatism, they left behind a record more honest than any parchment. A story of survival written in the only language the earth never forgets, the enduring whisper of stone on stone. Pollen grains might seem insignificant tiny specks barely visible to the naked eye, but locked within their microscopic walls lies an entire botanical history of our planet. These minuscule time capsules, preserved in the muddy depths of lakes and the oxygen-starved layers of peat bogs, carry the genetic blueprints of plants that thrived thousands of years ago. Each grain is like a coded message, its shape and texture unique to its species, allowing scientists to identify not just what grew in a landscape, but when and how those ecosystems shifted over millennia. Take the bogs of northern Europe, where layers of peat hold pollen records stretching back to the last ice age. In these waterlogged archives, a single centimeter of sediment might represent a century of growth, each stratum packed with pollen from plants long vanished from the region. One layer might be dominated by pine and birch trees that colonized the land as glaciers retreated. Higher up, oak and elm pollen appears, marking the arrival of warmer climates. Then, abruptly, the record changes. Tree pollen dwindles, replaced by grains from grasses and cereals. This isn't a shift in climate, it's the fingerprints of human hands. The sudden surge of wheat and barley pollen, alongside weeds like plantain that thrive in disturbed soil, signals the moment when forests fell to axes and the first fields were sown. What's astonishing is how precise these records can be. In the English fenlands, scientists tracing pollen in lake sediments pinpointed the exact century when Roman farming techniques transformed the landscape, introducing crops like rye and oats that left unmistakable marks in the mud. Similarly, in the Amazon, pollen from maize and manioc buried beneath rainforest soils revealed something revolutionary. Vast stretches of what we assumed were untouched wilderness were actually shaped by indigenous agriculture centuries before European contact. These grains don't just record nature, they document humanity's tangled relationship with it, but pollen's real power lies in its ability to reconstruct climates. Some plants are fussy, thriving only within narrow temperature or rainfall ranges. When their pollen appears in sediments, it's like finding a fossilized weather report. In Greenland, cores drilled from ice-free lakes show pollen from dwarf willows and wild roses during the medieval warm period, proof that parts of the island now too cold for such plants were once hospitable enough for Norse farms. Meanwhile, in Africa's Lake Malawi, pollen from drought-resistant grasses paints a picture of ancient megadroughts that pushed early humans to adapt or migrate. The most haunting insights come from sudden disappearances. In North America's Great Lakes region, sediments from 14,000 years ago contain pollen from spruce forests that abruptly vanish, replaced by sedges and shrubs. This wasn't logging or climate change, it was the work of behemoths. The disappearance coincides with the extinction of mastodons and giant ground sloths, creatures that maintained these open woodlands by trampling saplings and stripping bark. Without them, the ecosystem collapsed into something entirely new. Pollen, in this case, isn't just tracking plants, it's recording the absence of giants. Yet for all its resilience, pollen has a vulnerability. Modern agriculture and urbanization are smothering these natural archives beneath layers of fertilizer, concrete, and pollution. In some places, the pollen record of the 20th century is already muddled beyond recognition, a blur of invasive species and synthetic chemicals. That's why scientists race to extract these stories while they're still legible. Knowing each core pulled from a bog or lake bed is another chapter in Earth's grand, unread diary. And as we learn to translate these tiny botanical whispers, they don't just illuminate the past, they warn, guide, and sometimes humble us with the sheer endurance of life's quietest witnesses. Stromatolites don't just tell the story of life on Earth, they are the story, written in layer upon layer of living stone. These unassuming mounds, built by cyanobacteria over billions of years, are more than fossils, their time capsules still being crafted today. In Shark Bay, Australia, where turquoise waters lap against bulbous, rock-like formations, modern stromatolites grow at a pace so slow it's almost geological, just a fraction of a millimeter per year. Yet within their laminated layers lies a record of our planet's infancy, when the air was toxic to most life and the continents were barren. What makes these structures extraordinary isn't just their age, it's their simplicity. Cyanobacteria, some of Earth's earliest life forms, trap sediment with sticky filaments, then bind it with calcium carbonate, creating a new layer like a page added to a diary. Over millennia, these pages stack into domes and columns, each contour reflecting changes in sea level, climate, or even the bacteria's own evolution. The oldest known stromatolites, found in Western Australia's Dresser Formation, date back an astonishing 3.5 billion years. Their rippled surfaces, preserved in chert, capture moments when life was just beginning to shape the planet itself. But stromatolites aren't just relics. In Shark Bay's hypersaline waters, where few predators can survive, these microbial architects thrive much as they did in the Precambrian seas. Their survival offers a rare window into how ancient ecosystems functioned. The cyanobacteria within them still perform a miracle every day: photosynthesis, the same process that transformed Earth's atmosphere from a noxious mix of methane and carbon dioxide into the oxygen-rich air we breathe. In essence, every stromatolite is a memorial to the great oxidation event, the planetary revolution that made complex life possible. The real magic lies in the details. Cut open a fossilized stromatolite and you'll see bands of light and dark, not just seasonal layers but chemical signatures of the water they grew in. Some contain microscopic tunnels where ancient bacteria once moved, while others preserve the faintest traces of organic molecules, long-chain hydrocarbons that hint at the dawn of biochemistry. In the Bahamas, where modern stromatolites grow in shallow lagoons, scientists have found that their layers record hurricanes, with debris from storms sandwiched between comma periods of growth. What's humbling is realizing how precarious their legacy is. Once dominant across the planet, stromatolites were pushed to the brink by the very oxygen they helped create, a gas that allowed more complex life to evolve and eventually outcompete them. Today, they cling to existence in a handful of extreme environments, from Australia's salty bays to alkaline lakes in Mexico. Yet these survivors are more than curiosities. They're living benchmarks, helping scientists distinguish between abiotic rock formations and true fossils on other worlds. When NASA studies Mars' sedimentary rocks, it's stromatolite-like patterns they're searching for, the universal handwriting of life itself. So the next time you see a photograph of Shark Bay's stromatolites, remember, you're not just looking at rocks. You're seeing the closest thing we have to a portrait of Earth's childhood, a self-portrait sketched by microbes that turned a hostile planet into a home. And somewhere in those layered mounds, there's a lesson about resilience, about how even the smallest organisms working together across unfathomable time can change the world. Impact craters aren't just scars, they're cosmic autographs, signed by asteroids and comets that rewrote Earth's story in an instant. Take the Chicxulub crater, hidden beneath Mexico's Yucatan Peninsula. This 150-kilometer-wide pit is no ordinary dent. It's the smoking gun of the Cretaceous Paleogene extinction, the catastrophe that erased 75% of life on Earth, including the dinosaurs. But what makes Chicxulub extraordinary isn't just its size, it's the forensic evidence locked in its rocks. Drill into its center, and you'll find a layer of iridium, a metal rare on Earth but common in asteroids. This glittering dust, scattered worldwide, is the calling card of the 6-mile-wide space rock that struck 66 million years ago, unleashing firestorms, acid rain, and a years-long winter that transformed the planet. Yet Chicxulub is just one entry in Earth's violent guestbook. In South Africa's Vredefort Dome, the oldest and largest confirmed impact crater, the shock of a 200-kilometer-wide asteroid 2 billion years ago was so immense it warped the planet's crust like putty. Today, the crater's center rises in a haunting bullseye of melted rock, where temperatures once rivaled the sun's surface. Meanwhile, Arizona's meteor crater, younger and far smaller, offers a pristine snapshot of cosmic violence. Its jagged rim and ejected boulders show exactly how energy transforms geology in seconds, flinging 1,000-ton slabs like pebbles and creating minerals found nowhere else, like shocked quartz with its telltale microscopic fractures. The real detective work begins when craters hide in plain sight. Canada's Sudbury Basin, now a sprawling mining district, spent a century mistaken for a volcanic caldera until scientists spotted its true origin. A nickel-rich asteroid struck 1.8 billion years ago that left behind enough metal to supply industrial needs for centuries. Similarly, Germany's Nördlinger Rise crater masquerades as a picturesque valley, its true nature revealed only by suvite, a bizarre rock that's part melted glass, part shattered bedrock, forged in the hellish instant of impact. But craters don't just tell stories of destruction, they're also architects of opportunity. The Chesapeake Bay crater, buried beneath Virginia's coastline, altered groundwater flow for millennia, creating the estuary we know today. In South Africa, the Morokweng crater's platinum-rich deposits drew ancient civilizations long before geologists understood their extraterrestrial origins. Even life itself may owe a debt to impacts. Some theories suggest the heat and chemistry of early collisions helped assemble the building blocks of RNA in primordial soup. What's humbling is realizing how often Earth crosses paths with these celestial bullets. The Barringer crater in Arizona formed a mere 50,000 years ago yesterday, in geological terms, when a nickel-iron meteorite the size of a house slammed into the desert. And in 1908, the Tunguska event proved we don't always need a crater to feel the cosmos' wrath. A meteoroid exploding over Siberia flattened 2,000 square kilometers of forest with the force of 1,000 Hiroshima bombs. Today, networks of telescopes scan the skies for new threats, but the craters beneath our feet remind us Earth's memory is long, and its next cosmic encounter isn't a matter of if, but when. Yet for all their violence, these scars hold a strange beauty. In Australia's Goss's Bluff, indigenous traditions speak of a celestial ancestor crashing to Earth, her impact forming the crater's sacred rings. Science and story converge here, both acknowledging what the land has never forgotten, that sometimes the most transformative moments arrive from the stars. Geoglyphs are more than just giant drawings, they're conversations with the land itself, where human hands and natural contours collaborate to create something transcendent. Take the Nazca lines in Peru, sprawling across 400 square miles of desert. From the ground, they're nearly invisible, just shallow grooves in the earth. But from above, they transform into hummingbirds, spiders, and geometric shapes so precise they feel otherworldly. What's astonishing isn't just their scale, but how they work with the desert. The Nazca people didn't fight the landscape, they understood it. By removing the dark, sun-baked topsoil to expose the lighter clay beneath, they created lines that resist erosion in one of the driest places on Earth. The desert's own stability, unchanged by rain or wind for millennia, became their canvas. Then there's Ohio's Great Serpent Mound, a quarter-mile-long effigy coiled along a ridgeline. Unlike the Nazca lines, this earthen serpent wasn't just placed on the land, it embraced it. The mound follows the natural curve of the terrain, its undulating body mirroring the shape of the creek below. Archaeologists suspect its builders, whether the Adena or Fort ancient cultures, chose this spot deliberately. The ridge's elevation made the serpent visible for miles, while the underlying geology, a mix of clay and gravel, held its form against centuries of weathering. Even the serpent's alignment feels intentional. Its head points to the summer solstice sunset, weaving celestial cycles into the earth itself. But how do these massive artworks endure? The secret lies in the dirt. At Nazca, researchers analyzing soil compaction found that the lines weren't just scratched into the surface, they were engineered. The desert's natural cement-like crust, called pampa, was carefully peeled back in layers, creating a contrast that sunlight and shadow would accentuate. Meanwhile, Serpent Mound's builders mixed clay with ash and charcoal, creating a mortar-like binder that resisted erosion. These weren't haphazard etchings. They were feats of ecological understanding, where every scoop of earth accounted for wind patterns, rainfall, and even the angle of the sun. The purpose of these geoglyphs remains tantalizingly unclear. Were the Nazca lines ritual pathways, astronomical calendars, or offerings to gods who viewed them from above? Did Serpent Mound mark sacred ground, commemorate celestial events, or tell a creation story? What's undeniable is their dialogue with nature. The Nazca might have seen their desert as a living entity, its flat expanse a mirror of the heavens. The serpent's builders could have viewed their ridge as the spine of a primordial being, its curves echoing the rivers that shaped it. Today, these earthworks face new challenges. Climate shifts bring rare rains to Nazca, threatening lines never designed for moisture. In Ohio, invasive roots and modern agriculture test Serpent Mound's resilience. Yet their survival speaks to something profound. When humans listen to the land, when they work with its contours and rhythms, their creations outlast empires. These geoglyphs aren't just art, they're lessons in humility, reminding us that the most enduring marks aren't those we impose, but those we weave into the world's own story. Beneath the churning waves of the North Sea lies a lost world, one where mammoths once roamed river valleys and human hunters tracked herds across grassy plains. Doggerland, the vast Mesolithic landscape now submerged beneath 60 feet of water, wasn't just a bridge between Britain and mainland Europe. It was a thriving ecosystem, home to forests, wetlands, and possibly thousands of early inhabitants. When fishermen trawl these waters today, their nets sometimes haul up more than fish antler tools, flint spear points, and even carved bone ornaments emerge from the silt, artifacts untouched since the day rising waters forced their owners to retreat. These aren't mere relics, they're pages from a drowned history book preserved by the very sea that swallowed them. What makes Doggerland so extraordinary isn't just its scale, stretching from Scotland to Denmark at its peak, but how vividly its secrets are emerging. Sonar mapping has revealed submerged riverbeds snaking across the seafloor, their curves mirroring ancient watersheds. Core samples contain pollen from oak and hazel forests that flourished when sea levels were 300 feet lower, while the bones of aurochs and brown bears paint a picture of a landscape richer than modern Europe. Most haunting are the human traces. A deer antler harpoon found near Rotterdam, its barb still sharp after 8,000 years, or the recently discovered Doggerland footprints, compressed mud layers that, when scanned, show the barefoot tracks of adults and children threading between long-vanished marshes. But Doggerland isn't alone. Off Florida's coast, the drowned karst springs of the Paleo-Indian period preserve stone tools and mastodon bones in crystal-clear aquifers, their depths sealed like time capsules. In the Black Sea, anoxic waters below 200 meters have perfectly preserved Bronze Age shipwrecks, their wooden hulls and coiled ropes intact as if sunk yesterday. Even more astonishing is India's Gulf of Combat, where sonar images suggest sprawling stone structures beneath the waves, potential evidence of a settlement predating the oldest known cities by millennia. Each site shares a common thread. Rising waters didn't destroy these landscapes, they froze them in time, shielding them from the erosion and decay that ravaged sites on land. The science of reading these submerged archives is as delicate as the ecosystems they document. Divers in Denmark's fjords use vacuum tubes to extract DNA from sediment layers, reconstructing entire food webs from genetic fragments. In Australia's Northwest Shelf, archaeologists pair indigenous oral histories with bathymetric maps to locate freshwater springs that once sustained now drowned coastlines. Meanwhile, off Japan's Yonaguni Island, debates still simmer about whether steppe terraces and right-angled formations are natural or the remnants of a lost civilization, proof that these watery realms blur the line between geology and human story. What's urgent is recognizing how many of these archives are at risk not from the sea, but from our own activities. Bottom trawling shreds delicate stratigraphy, while underwater mining and pipeline construction scatter irreplaceable context. Even well-meaning treasure hunters can disturb the chemical balance that's preserved organic materials for millennia. Yet when protected, these sites offer unparalleled insights. The submerged cypress forests off Alabama's coast, for instance, contain tree rings that chronicle droughts older than the pyramids, while the sunken mangrove peat beds of Indonesia hold clues to ancient tsunami patterns. Perhaps the most poignant lesson from these drowned worlds is their relevance to our future. As modern sea levels rise at unprecedented rates, the ruins of Doggerland's marshes and Florida's springs become more than curiosities, they're mirrors. They show us how cultures adapted or didn't when shorelines advanced, how ecosystems migrated, and what happens when the slow creep of water becomes a flood. The same forces that preserved these landscapes, rising seas, shifting currents, are the ones we now face, and somewhere in the silt and submerged peat, there might just be a map for what comes next. From tree rings counting centuries to ice cores trapping ancient air, and from petrified forests frozen mid-growth to cities sleeping beneath the waves, Earth's archives aren't locked away in vaults or buried in distant caves. They're all around us, woven into the very fabric of the landscapes we walk through every day. These silent storytellers hold memories of worlds we can scarcely imagine, climates that shaped civilizations, extinctions that reset the clock of life, and moments when the sky itself rained fire. Yet for all their grandeur, these records share something humble in common. They weren't created for us. The Earth remembers because that's simply what it does, layering time like sediment, one era atop another, with or without an audience. What makes these archives so extraordinary isn't just their age, it's their honesty. A stalagmite doesn't exaggerate rainfall patterns. A Packrat midden won't gloss over a drought. They tell their stories without bias, offering us something rare in human history, an unfiltered truth. When we compare the isotopes in a coral skeleton to the rings of a millennia-old oak, or match volcanic ash in Antarctica to legends of lost cities, we're not just piecing together the past. We're learning to speak Earth's language, one that doesn't rely on words but on chemistry, layers, and time. And here's the beautiful paradox: the more we uncover, the more we realize how much we've forgotten. Indigenous cultures often understood these archives intuitively, reading the land as a living text, where the shape of a river or the health of a tree carried meaning. Modern science, with its ice core drills and mass spectrometers, is in many ways catching up to this ancient wisdom, just with different tools. The Yupik people of Alaska, for instance, have oral histories of coastal lands swallowed by the sea, now confirmed by submerged peat beds and pollen records. Similarly, Aboriginal tales of fire mountains align perfectly with volcanic ash layers in the soil. These aren't coincidences, they're proof that human memory and Earth's memory have always been in conversation. But these archives aren't just about looking backward, they're compasses for the future. When we see how quickly ice sheets retreated in the past, or how ecosystems collapsed under pressure, we're not just studying history, we're reading a roadmap. The methane bubbling from thawing permafrost, the bleaching bands in coral skeletons, even the shifting pollen in lake sediments, they're all flashing signals, warning lights in a planetary dashboard we're only now learning to interpret. The Earth isn't just reminiscing, it's whispering urgent lessons to anyone willing to listen. So the next time you press your hand against the rough bark of an old tree or skip a stone across a pond, remember this: you're touching more than just the present. You're brushing against deep time itself, a continuum that stretches back billions of years and forward into mysteries we can't yet grasp. These natural archives don't belong to scientists or historians. They're part of our shared inheritance, waiting in the quiet corners of the world for curious minds to uncover them. And if there's one thing they teach us above all else, it's that we're not separate from this story. We're characters in it, leaving our own layers for whatever or whoever comes next. If this journey through Earth's hidden memories has sparked your curiosity, hit that like button and subscribe to join us as we keep unraveling the planet's greatest mysteries. Drop a comment below. Have you ever stumbled upon a piece of natural history in your own backyard? A fossil, an oddly shaped rock, or even an ancient tree? Let's keep the conversation going, because every discovery, no matter how small, adds another line to Earth's unfolding story. Thanks for watching, and we'll see you in the next